So now we're going to look at some properties of the Fourier series. And the first one we're going to look at is the idea of scaling. So what we're looking at here is what would happen if we have a time sequence and we have a square wave as we had before, and we're still going to have the same period of big T between our square waves. But before, where we had an equal period where the time that we had the square wave was up, was the same as the time it was down, we're gonna change that. We're gonna say, what happens if we vary the width of this pulse? So I'm going to determine the width of this pulse to be a variable tau. And so now our pulse will range from minus tau on 2 to plus tau on 2. So our pulses occur at the same regularity, but now they're going to be different. They're going to be different in their width. So if we go to evaluate our C of n, we've got 1 on t. We still average over the whole period, so it's still 1 on big T. But now we're going to integrate from minus tau on 2 to tau on 2. X of t is the same. We'll assume that this is an amplitude of 1, so it will still just be e to the minus j n omega naught t dt. And that's going to be our integral to look at. So if we go through that integration, we end up with 1 on t, 1 over minus j n omega naught, e to the minus j n omega naught tau on 2 minus e to the j n omega naught tau on 2. So when we get to that point, we can then substitute in for big T, and so we will end up with 1 on t, 1 over minus j n, we put 2 pi big T on the top for our omega naught, and e to the minus j n pi t on big T minus e j n pi tau on big T. These t's will cancel out, which is handy. And we can say C of n is going to be 1 on pi n sine n pi tau on big T. Which is going to be our tau on big T sinc n tau on big T. So we have our sinc function. Now this is exactly the same as we got to when we did the Fourier series before, except we now have this value of tau. And so what is this actually going to do? So tau appears twice. It appears once on our amplitude term. So for example, when n equals 0, that tells us our C0, or DC term, is going to start from tau on big T. So when n equals 0, this sinc term goes to 1, we get our term here. We're still going to have this sort of sinc shape with a number of lines in it, but tau now is a multiplier of our frequency, and so our sinc is going to go through 0 now at 1 on tau. Our spacing between our lines is always going to be the same. As before, our spacing between our lines is going to be determined by the period. So we always have a value of 1 on t between our lines, but our shape, our sinc shape, is now determined by this 1 on tau. So this shows us an important thing about how changing the width of our or period of our spectrum actually changes our Fourier series. So what we see from this is if we change the period, and by changing the period I mean it's this t here, we change how regularly our pulses come, then our lines get closer together. So the further apart the pulses, the closer together our frequency lines are. And then the shape is determined by the width of our spectrum. So 1 over tau. So as our pulses get narrower, so tau gets small, 1 over tau is going to get big, and our Fourier spectrum is going to spread out. So let me just draw that out here. So let's look at scaling the pulses. So what this is saying is if we have very narrow pulses, okay, again our period is still t, then what happens with our Fourier spectrum is that we will end up with 1 over, when tau is now very small, our Fourier spectrum is going to get quite big. Our lines will stay the same because our lines are determined by 1 over big T, but this point determined by 1 over tau is going to get quite wide. Conversely, if we have a large tau, again my drawing's not very good but I'm trying to keep the T the same, what's going to happen is our 1 over tau will get narrow and we'll end up with a much narrower spectrum. Again, our lines will stay at the same width, 1 over big T, but our tau now becomes much closer together. We should also note that our height is going to change. So as tau becomes small, tau over big T is going to change, whereas this height is tau over big T. Now that is very important because that comes about from the fact that the energy in our spectrum here, this is in F of course, has got to be the same to the amount of energy that's in our time domain. We're just looking at a different representation here. We're not changing anything. So there must be an equivalence of energy between these two. If I manage to create energy in this transform, then I've done something wonderful, but I've broken the laws of physics. My energy must be the same. So if my pulses are narrow, there's less energy, this is going to shrink. If my pulses become wide, there's more energy, this is going to increase, as tau on T shows us here.